In this video, I wanted to start by working with some of the basic properties of limits that have been listed above in the notes. And I've started with two really basic examples, just as an opportunity to discuss a couple of those properties. So first, the limit as x approaches 5 of 10. So the broader scenario that I want to consider here is when you have the limit of a constant function. So whatever we have inside the limit here, I'm going to call it f of x. So in this case, we're taking the limit of the function f of x equals 10. Oops. Sorry, it's a little sloppy there. The graph of that function, you might remember, would be a horizontal line that goes through 10 on the y-axis. So if you consider the limit as x approaches 5 from the right or from the left, well, the y value is just sitting at 10. And so as x approaches 5 from either side, then the y value is approaching 10. And in fact, the limit of any constant function, so whenever you have a constant here, will be equal to that constant, no matter what x is approaching. So if x was approaching negative 3,000, if you have the limit as x approaches negative 3,000 of 10, the limit is equal to 10. Okay. Now the limit as x approaches 5 of x. So let's say now that we're taking the limit of the function f of x equals x. I'm going to look at that one in terms of a table. So suppose we make a little table of inputs. So we want x approaching 5. So we pick values close to 5, 4.9, 4.99, 4.999. Approaching 5 through values less than 5, and approaching 5 through values bigger than 5, so 5.001, 5.01. Okay, you get the idea. Well, if we're inputting these x values into the function f of x equals x, then the output is just equal to the input. If x is 4.9, f of x is 4.9. If x is 4.99, f of x is 4.99. Okay, well, so as x approaches 5, the f of x, which is equal to x, must also approach 5. And so the limit here is 5. And taking a step back, the lesson learned is if you're taking the limit of just x, that'll be equal to whatever x is approaching here. Okay, so now I want to take those two really fundamental properties along with some of the other properties that I had listed above and take the limit of a polynomial. And I want to approach that first, kind of step by step, applying these properties one at a time. But then we can make a broader inference about limits of polynomials. Okay, so I'm going to rewrite that example over here. The limit as x approaches negative 2 of 3x squared plus x minus 8. Okay, applying those properties one at a time. So first of all, when you've got a sum of two functions inside your limit, you're allowed to separate that into the limit as x approaches negative 2 of the first part of this sum, so the 3x squared, plus the limit as x approaches negative 2 of just the x here, and then minus the limit of that last piece. So there is a property of limits that says you can separate out, when you have addition or subtraction, you can separate out limit of the first part plus limit of the second part. And that's actually also true for multiplication and division. So whenever you have those basic operations inside of your limit, you're allowed to take the limit of each piece individually and then add, subtract, multiply, divide the result, whatever the operation is. Okay, so a couple of these we can evaluate right now from those properties we just discussed. Right here, you've got the limit of a constant, and so that's always just equal to the constant, so in this case 8. Right here, you've got the limit of just x, and so that's always equal to whatever x is approaching, so in this case negative 2. Okay. In this first part, when you have a constant multiple like the 3 here, you're allowed to move that out front. So this is equal to 3 times the limit as x approaches negative 2 of x squared. there's another property in your list that says when you have x to the n inside your limit, you're allowed to just substitute in the value that x is approaching. So this is equal to 3 times negative 2 squared. When you have a power of x, you can just substitute whatever x is approaching into that expression. And then we've got the rest of this, minus 2 minus 8. And so now we can just do the arithmetic. So this is 3 times 4 minus 10. So this is 12 minus 10. Our final answer is 2. Okay, but a polynomial, by definition, is what we call a linear combination. But so you're adding or subtracting positive integer powers of x. And so when you take the properties that are in the list and put a few of them together, you find out that you could take the limit of any polynomial by just plugging in whatever x is approaching, which that's what amounts to everything I did here. Basically, overall, what happened is we substituted negative 2 for all the x's. If you look at here and then focus on this step down here. So 3 times negative 2 squared plus negative 2 minus 8. And so there's a theorem in the notes there that says the limit of any polynomial function is just equal to p of c when you have x approaching c.